What I'm going to talk about today is a journey to 1 terabyte per second with Ceph. And this was one of the most fun and also stressful projects I've worked on. And this all started with a really, really good customer. These guys came to us with a very interesting use case. And they already had kind of designed a rough architecture for what they wanted, but they wanted advice from us. And so, if you're thinking about building a fast Ceph cluster, it's really good to bounce the ideas off somebody first, because there's a lot of different views on it, and it can be really good to just get advice. And we loved it because it meant that we had a lot of input into the design here. They already had a very, very fast network infrastructure in place, and I can't tell you what it was. But what I can tell you is that I really liked what Bloomberg was doing earlier. So, talk to them about that, because it's a very good way to do things. Okay, so let's see. These guys had a couple of constraints that we had to work in. The hardware had to be Dell, and that's fine. Dell has some good boxes out there. Yeah, we were fine with working with that limitation. We were limited to 4U per rack, spread over 17 racks. That's what they wanted for failure domains. Fine, not too bad. Per rack power limitations. Originally, they told us 1,000 watts. That's 250 watts per node. That's a little rough. After talking to them and after kind of looking into things, we had a target of more like 1,500 watts. That wasn't so bad. So, not horrible. But the bigger disruption, or the bigger issue, was that they didn't want any disruption at all during the hardware upgrade. They were already on an HDD-based cluster. They wanted to migrate to an NVMe-based cluster with 0 downtime. So we helped them get there. All right, so you just saw a really, really good presentation from Bloomberg, especially around NUMA tuning and setting all of that up. That's complicated. It's hard to get that right. You can, absolutely, you can do it. Our preference is to build single processor nodes, or single socket nodes, just because you can get away with a lot more doing it that way. You still can absolutely benefit by doing NUMA tuning in the BIOS and setting up separate zones, but you can kind of get away to some extent without. It's a simpler setup, but it's a little bit of a slower setup in terms of not tuning that, but it's still pretty good. We like to give Ceph a generous amount of CPU cores. We see a lot of people skimping on this, but at least for Ceph, especially if you're doing NVMe, it's really worth it. And we also like smaller nodes that have fewer drives. So one of the things that's really interesting, and this actually touches, Tyler, I think on what you were seeing with CRC32C, Ceph uses a lot of memory bandwidth. This is something that we've been looking at a lot more recently, but we can consume about, just for big 4 megabyte reads, a really easy workload, we can consume about 6x the memory throughput relative to what the OSDs are actually reading from disk. And more surprisingly, on the client side, we're seeing closer to an 8x memory throughput amplification. It's actually significantly worse for random reads, small random reads and small random writes, but the overall memory throughput, overall throughput in general is a lot lower, so it doesn't quite matter as much. But this is why we're starting to see on more modern processors with lots of channels of memory and lots of, and very fast memory with DDR5, Ceph is doing better. We're kind of, brute forcing our way out of some of that problem. But it's still gonna be a really big problem as we start going towards 200 gig E, 400 gig E, it's going to show up again. So let's see. Since I'm time limited, I'm just going to kind of skip this slide, but it's basically what we were just talking about. So okay, this hardware design that we came up for them, it actually looks a lot like what a lot of vendors are doing right now, with the exception that we're using 100 gig E. A lot of vendors are moving towards 200, but overall, this is kind of the sweet spot that we came up with in terms of price, performance, everything. Is running, actually, testing was done with Focal, Ubuntu Focal, and that was only because that's what they're using in their environment. There was no other real reason for that. So, okay, the plan for this: upgrade the existing cluster to Quincy, deploy new hardware, install CBT, which is the performance framework we use for testing Ceph and evaluating, rapidly running tests and evaluating the hardware, and then redeploy this using Dan's upmap remapped tools, which he'll talk about later today. So, okay, one of my colleagues, Toby, did this upgrade, and it all went great. Ceph ADM worked wonderfully for it. The customer deploys the new hardware. There was an issue where they accidentally deployed the OS to the OSD drives instead of the BOS card for the, yeah, exactly, right? So that unfortunately during the initial testing kind of it was a little bit of an issue, but basic testing on this looked good, network looked good, drives looked good. What could go wrong? Okay, so one of the things that was actually really nice about this hardware is that it's basically an upgraded version of what we have in the upstream Ceph test lab. So we were able to try and get not exactly apples to apples, but sort of close comparisons. There's a lot of data that we've got already on these older Rome-based processors and Dell R6515 chassis. So not exactly, but it gave us at least a benchmark to try to hit. And these were the first results we got. Really, really quite bad. It was not good in any way. So what happened is we basically went back and started doing like single OSD tests, single node tests, looking at the behavior of even just individual tests on these systems. It was quite painful. One false lead that we had was that we were seeing the CCT complexes like hitting 95 degrees Celsius, and we thought this was like a thermal overloading problem, but it was not. That was totally fine. Well, not really, but it wasn't causing the problem. One of the really strange things that we saw is that we could get good performance out of the drives for like, individual drives were great, and then as you scaled up to multiple drives, performance would tank, and it wouldn't come back for about a half an hour, and then it would magically be okay again. Yeah, I know, it's just like gremlins in the system. So there were three things eventually, after all this pain, that we figured out. And the first is an easy one. We've known this for many, many years, that disabling C states yields a really, really big performance boost. And I don't remember who it was that first figured this out. It might have been Nick Fisk or possibly Stephen Blinick at IBM. But one of those guys, I think, was the one that first figured this out. And it's really, really good. You can either do that in the BIOS, usually. With Dell, it's, I think, maximum performance mode in the BIOS that does this. Or you can use the tuned admin to set like network latency mode or one of the other modes that also disables C states. So there's different routes for that. The big one, though, actually, and this is something that the customer figured out, not us, was that disabling IOMMU actually fixed that very, very strange problem that we saw where the performance of like running multi-drive tests would tank everything and then come back. We've tried to talk to AMD about this and have not gotten a whole lot of response back. So I think we've got someone possibly, I won't pick on you here, but I would love, if anyone has contacts in AMD that works on a team that does this kind of stuff, I would very, very much like to get in contact with them. But yes, so the customer had actually seen this in other contexts too, and they had kind of a hint that that was what was going on. So fix that, and then we've got the infamous upstream Debian Ubuntu build issue. So I was the author of that Ceph article. And yeah, actually the canonical guys had figured this out like 4 years ago as well, I think. I don't know if it was independent or not, but yeah, they had posted about it, and that's where I got the hint that, oh, hey, this isn't good. We should look at this. And it actually turns out that they had read an older, like, commit that I had made for do CMake, where we had like changed how the build works, and we had broken performance in all of the like compiles that you make. And then we had put a note in there, oh, hey, when you use do CMake, do this. And they took that, saw that, fixed their builds, and then we never fixed upstream. So like, it happens, right? But definitely if you know about it, if you know about the kind of stuff like this, tell us, please. All right, so let's see. After all these fixes, everything was much better. Not as good as I wanted it for random writes, frankly, but here we're only testing 3 nodes versus 5 on the upstream lab, even though it's a almost comparable number of drives. So the results look a little low, but there are fewer drives and fewer nodes, so it's not so bad. All right, so this took us up to winter break. Had a nice tropical vacation and came back all ready to go. But at the start of 2024, we actually got hit by another customer cluster that was in crisis and had to spend about maybe 4 days of the first new year doing that when we were hoping to do all of this. And yeah, everything was backing up to the point where they needed to get data migrating the following Monday. So we didn't actually start doing any kind of scaling tests until Friday, and then worked over the weekend to make it all happen. But luck changed. It was really, really a turning point in this. With the new settings, 30 OSDs looked really good. Jumping up to 100, we saw pretty much linear scaling. Jumping up to 320, we continued to see linear scaling. It was really, really kind of amazing to watch that happen. These tests right now are with half of the cluster serving as OSDs and half of the cluster serving as clients. When we started this, I knew I wanted to try to hit a terabyte per second with this cluster. I thought it could be done. But to do it, we'd have to run the clients on the same nodes as the OSDs. And if you remember looking at like the memory throughput numbers, that starts getting a little dicey. You've got a lot of memory overhead, a lot of write amplification happening because now you've got clients and OSDs on the same servers. So we did it. We did those tests over the weekend. We did a lot of like screwing around to just get over the hump. We were sitting about like 950 gigabytes per second for a while. And we ran into some very strange issues when we did this. I think I covered most of it in the blog article, so I'm not going to really do it here since I'm starting to run out of time. It's not too bad. But yeah, definitely look at the blog article and feel free to ask me about it if you want. But we were able to actually get a terabyte per second, at least in the 3x replication case. As you can see here, for writes, far less, makes sense. 3x replication, we're not going to go that fast. We're a little bit worse in aggregate than with reads, but that also kind of makes sense because the drives aren't as fast at writes as they are with reads. IOPS, not terrible. I would like to get this higher, but still, I don't think anyone's published numbers bigger than this, so I'm happy with them for now. The erasure coding case, though, is interesting. This is what they're actually using in production now. They wanted to use 6+2 erasure coding. Our read performance was hit quite a bit, and I think that's primarily due to network. Now, all of a sudden, we're doing a lot more read transfers over the network. It's hitting us harder. Writes actually go up fairly significantly, and that's also because now you're not doing 3 writes for every write. You're just doing a subset of that. I don't want to do the math in my head, but much less. Random reads and random writes, of course, go way down. There is a PR that's in the works that a good friend of mine, Radek, is working on right now that is going to dramatically improve this. This was actually an old PR from about 5 years ago that was submitted from a guy in China. And we kind of dropped the ball on it, frankly. No one did a really good review of it. And we went back and kind of looked at it. And I did some testing about last summer. I basically just got his PR into good enough shape to put it into main and get it running. It wasn't really ready to be merged. There was a lot of work that needed to happen on it, but the results looked really good. And Radek took it and ran with it, and now it looks like we're probably not going to get it in for Squid, but there's a pretty good chance that we'll get in for a point release or at least for Tentacle. So I expect the read numbers there for erasure coding to at least double in this case. What was that? Yeah, this is erasure coding with RBD. Yeah. So if you look at how the per node performance scaled, we were actually maxing out the network here. We were able to as long as we had clients on separate nodes and weren't co-locating them with the OSDs, we were hitting about 20 gigabytes per second. When we co-located them, that dropped, but not horribly. It was like 20% less, roughly 20 to 25%. I think that if we could reduce the memory bandwidth overhead, we might be able to make that better. and we need to anyway. So that's, I suspect what we were seeing there. Otherwise, the random read and random write IOPS were okay. We see that we often hit a limit of around 600,000 random read IOPS per node. I have seen this over and over and over again, regardless of the number of NVMe drives. I believe we're seeing contention with the kernel TCP stack. And so I'm actually working with a couple of folks right now at NVIDIA to see if we can reduce some of the contention there. But that's very, very early. So we'll see what happens. But I'm hopeful that we'll see an improvement there. And potentially, other TCP stacks, outside of the kernel might also be better. But we'll see. Okay, so wrapping this up, Clyso handed the nodes back to the customer for reimaging. My good colleague Toby integrated all of the new OSDs. We used Dan's upmap remap script to assist in the migration, I guess. Maybe is the right way to say it. And yeah, within 2 weeks, we had the entire thing moved over. They saw some immediate benefit to it. They basically said they were thrilled and now needed to work on optimizing their application to make use of all of this extra performance. And yeah, we have gotten some interest in other people that want to do the same thing. So this is exciting stuff. And I'm convinced that if we can kind of band together as a community and start looking at this stuff, I think we can beat VAST. I think we can beat DDN, Weka, everybody. Like, I've seen some of their numbers, and I think there's a pretty good chance that we can at least hit the same numbers they do and maybe do better. So anyway, that's it.